what we do have in solar energy is a known and commercially available techniques to have storage. So heat can be stored. And this is what we do in solar plants. What we have, we generate electricity in the morning, and at noontime, there is enough power, enough energy that is generated or collected from the sun. This energy can be stored. Therefore, during the day, you manufacture enough electricity, and this electricity can be monitored to be very steady, unlike the power that is generated from photovoltaic or wind. This is very steady. And this energy that is stored can later be used to generate power in the evening or at night when you don't have solar power. So actually, if you design it correctly, you can generate enough electricity throughout the day just by using storage capability. The other, actually this storage capability is considered to be the holy grail of this solar thermal, because this is the main advantage of solar thermal plants. The other capability is to be able to use it with as hybrid plants. What they do today is they make these plants use, and they also add to the ability to heat the steam using a gas-fired boiler. Actually, you just heat the steam, so you don't need just solar energy. You can heat it in any way, and to make sure that your production is always at 100% or the availability that is required from power plants, from the base load power plants, you can hybrid it with natural gas ability. One last thing before we talk about concentrated solar power, I want you to be reminded with a factor that is called the cosine effect. This cosine factor, I will talk about it later, and I will show you how it influences the efficiency of solar thermal, is the fact that the sun, if you take a flat panel that is, its surface is its surface normal is not directed toward the sun, but it is located with an angle towards the sun, this angle create an actually affect the amount of energy that's fall on this surface. So this is the amount of energy that's reached from the sun. As I told you before, this factor, let's say this is 1000 watt per meter square. What actually reaches the surface is this 1000 multiplied by the cosine of this angle. So this is the actual radiation, solar irradiance that fall on the surface that you use. Okay, so let's describe now several technologies for concentrated solar power. And I will start with the most common one. This technology, known as draft, actually is used since the 1980s by a company named Luz, that's built, an Israeli company, that's built it in the Mojave Desert, near a facility of 354 megawatts that generate 354 megawatts of electricity, which meets the power needs of about 500,000 people, and it's located in the Cornell Junction in California. This very giant, you can see here the size. Giant, this is a person size, and this is the size of the parabolic mirror. They concentrate their energy through to this receiver, this pipe here, which holds the high thermal fluid that later is used to generate the steam. And few companies in there, you can't see it, but the first company I want to mention is called Soler. And Soler was acquired by Siemens for $400 million in October 2009. And the other company, big company that's manufactured many fields of solar thermal is Solar Millennium. And there, I just checked, their value is about, what was it? Also about $400 million value, and they are public now. So how does it work? First, in the morning, you see here the sun, you can follow the date by looking at the sun here. So in the morning, heat is generated and the high thermal fluid that's run in these pipes that I showed you before is heated from about 290 degrees here to about 380 degrees here, and this heat is used, and later through a heat exchanger, it's transfer the energy, its energy, to the steam, to the water that are running here, and this steam that is generated here is used to run the motor on this side. Later on, this steam is cooled down and is run, and then again heated and run again. And the energy that's used and the high thermal fluid that's hit this steam is coming back to our system at lower temperature and again runs through this parabolic draft system. Then at noon we generate enough energy, as I told you before, that part of the energy is going through another heat exchanger that's used. This heat exchanger is transferring energy from the oil that is used, the high temperature fluids that's run through the pipes of the draft. This energy is used can be stored in a molten salt tank. These tanks, two tanks, one of them is hot tank and one of them is cold tank, contain molten salt. So this molten salt can store the energy that we transfer to it. So the salt is transferred to the heat, and here it's stored at 380 degrees temperature, and here the salt is taken from here and it's stored here, and the fluids come back again to the loop as cold. So at noon, part of it is stored, part of energy is stored, and part of energy again goes to the heat generation. What happens in the evening? In the evening, we don't have enough heat that's generated from this side, so we use partly the heat that is stored in the storage facility and use it together to generate the steam at this point. And then at night, we only use the energy that is stored in the storage facility to generate heat. And if we plan it correctly, as I told you, we can generate enough heat to store it for several hours and even throughout the night. Although people are debating regarding what is the most efficient way to do it. If we only need to go 3 hours with it, or 4 hours, or 2 hours with the storage capability, and later on use the hybrid operation to generate the heat at night. So what are the problem of draft, or one of the problems of draft, is this cosine factor that I told you. So if we align this system in the north-south axis, when we follow the sun at high latitude, the sun is not directly above us. The sun is not above our head. So although in the morning we can follow the sun, at high latitude, usually in the winter, the sun is more on the horizon. So I'm telling you, this draft only has one axis tracking ability. So they only can move from side to side as one axis. So there is an angle between the sun and the aperture. And this angle, this theta, as I told you, vary the amount of solar energy that is collected by the draft. This is why if we calculate the efficiency, the monthly optical efficiency of draft throughout the year, we can see high variation between summer, where it's reaching its peak, to winter. And this can be a major problem when you want to have a power plant that generates electricity throughout the year more or less steadily. So, disadvantages of draft, as I told you, the single axis tracking limit optical efficiency. There is about 45% difference in performance between winter to summer, mostly if you use this north-south axis alignment. Moreover, I didn't talk about it, but this receiver, as you can see here, this is large, this is zoom in to this receiver. This receiver has a very large surface area, so it increased heat losses and limit operating temperature. This is why we can only use it between up to 380 degrees. You cannot heat the fluid inside this receiver to a higher temperature. I didn't say it before, but these turbines, this generator, are much more efficient when the heat that's used to generate the steam is higher. So the efficiency of the turbines is more efficient if is higher if you can reach higher temperature, and this limits trafability in this method. The other thing is this receiver is very complicated. It has high maintenance cost. Also, you don't see it here maybe, but these are moving joints, and they reduce the reliability, and they are hard to maintain. Usually when there is high thermal fluid that's running through them, and you need to maintain the ability of the joints to move all the time, all the day, because throughout the day, these joints are moving. So the second configuration that is considered today, people, mostly if you go to Brightsource website, they are considered with higher efficiency, or not efficiency, but more costly effective. So in this tower-based system, all the solar energy is transmitted optically to a small central collection region rather than being piped around the field as hot fluid. So these are used, you can reach, because all the energy is concentrated in one point, you can reach high temperature. And they talk about temperature of between 540 degrees to 840 degrees. And this is why they think they can be more efficient in the future. Actually today, what limits them is the storage ability. Today they can reach storage ability for 540 degrees, but they cannot yet, there is no any commercial available storage capability of 840 degrees. This is one of the things that researchers are working on. But again, because of this high temperature, they say they can reach large power levels, yet need to be proven. Unlike the trough, which is available, I'm telling you, available since the 1980s, and this is why they can say, okay, trough is bankable. The people can put money on it because they know it works for 30 years. This is very important. PV is not, people do not know yet if PV can work for 20 years. This is what they say they do, but they don't want it because it doesn't work that long. There is not enough data collected about it. However, regarding trough, there is enough data. There's a working place, a plant, as I told you before, in California, that generates now 354 megawatt of power, electricity. So tower has these issues as well. There is no one tower available today that's for enough time to generate this energy. For example, here you can see the first central receiver plant in Seville, Spain, PS10, that generates 10 megawatt of power. And here you can see another one that is new, made by eSolar, which generates about 5 megawatt power. So this one, this field, we'll talk about the disinvention later.
Well, I just wonder how tall that tower is.
So this one is about 110 meter, and this one is about 50 meter tall. And one of the problems they have now in California, they're saying this is not environmentally friendly because of the height of the tower. So people may think about it as a problem in California. Two companies that I want to mention in this sense are Brightsource Energy. They came out from Luz. Luz was closed at that time in the 80s or early in the 90s. They were closed because people didn't appreciate solar energy that much at that time. And the people who were engineers there later on founded Brightsource Energy, which was funded by Google, by Alstom, by other companies as well. They funded about $300 million in this company. And they won several major contracts in China. China is the most emerging field. 80% of the solar power plants are planned today are in China, actually. And the other company, which you can see it, is eSolar, that's invented also by Google Energy, about $200 million worth of money. Again, this company needs a lot of money because they to manufacture this high tower, this is about $10 million, just this tower. And the field is very expensive, but yet they think that along the line, this would be more efficient than trough. So let's talk about the cause and effect and optical efficiency of tower plants. So here is the tower. We have different heliostats, these mirrors throughout in the field. In the morning, let's say this is the morning, so you have a north field that's directed towards the receiver. As you can see, the theta, this angle, is very small. You direct from the sun, and therefore the losses of this mirror are very small. However, the ones in the south field, the theta is very large, and you lose most of your energy because of this effect. You don't use the whole ability of your mirror to collect the light and to transfer it to the receiver. Due to this, but however, because the mirror can be used in dual axis tracking system, they are not following just in one axis. You can maneuver them either this way or this way, so they can follow the sun pretty good. This is why the efficiency is more or less stable throughout the year. Not as high as the trough in summer, but not as low as the trough in the winter. And this, what you see here, is taken from the what we calculated from e-solar field. Two other factors that we need to consider in tower configuration are, first of all, blocking and shadowing. As you can see, the sun can be blocked by, let's say this is the heliostat, and this is transferred to the tower. The sun can be blocked by one adjacent heliostat, or another heliostat can shed a shadow on the heliostat, and therefore not all the sun radiation reaches the heliostat and transfers to the tower. Another problem is the visibility, the attenuation effect. If I show you here, you see this distance, this is the PS10 field that I told you before. This distance here, from here to here, is about 1 kilometer. Actually, it's 800 meters. So if we go back, there is about 1 kilometer, there is much attenuation through the atmospheric scattering from the mirror to the receiver, and this can be this also needs to be considered when you talk about large tower configuration. Let's talk about the disadvantages of tower. So first, as I said before, there is poor optical performance of far heliostat. Every set of heliostat is different. You need to construct, to focus the light to a different distance, so therefore the heliostat is a little bit different. Also, the land usage increases with distance from the tower, because you need to avoid this blocking or shadowing effect. You need to have large distance between the last rows at the end of the field. It's not modular. Once you build this field, it's not modular. You cannot say, okay, now I build this PS10, I can build another PS10, most likely, but to build PS20, for example, for 20 megahertz, for 20 megawatt, it's much different. The receiver is different, the height is different, it's a different project, and it's not modular as the trough. The trough, one of the advantage, you just add another row. Okay, you want another field, you add another row, you have another set of energy collectors. And the tower here is a very expensive component, and it has no cost reduction horizon. Usually, mostly if you go to a higher energy receiver. So now let's talk, I will introduce you to the project that I was involved with, which is concatenated micro tower. So we wanted to take advantage of the advantages of both trough and tower, and and to answer some of the disadvantages I described you earlier. So first, as I told you before, trough has large aperture, and it's inefficient tube because the large dissipation of heat. Again, another thing, it has single axis tracking, and it is expensive, and it doesn't follow the sun throughout the year, so the efficiency throughout the year is not the same